the topic of the talk today is concurrency in Deephaven, right? So the main goal here is to talk about how concurrency functions within the engine, how users of Deephaven should think about concurrency, whether they work here or are external users, and kind of some best practices for how to use the engine concurrently, right? So well, I have to switch the tab. The intended agenda here is first talk about the update graph processor, then second to talk about kind of how that parallelizes internally, move on to talking about locks, waiting for table changes, and then moving into logical clock and how the graph processor divides the world into cycles, or divides time into cycles, right? And then kind of more advanced topics around concurrent snapshots and initialization, and then getting on to a little bit, what you might care about from a unit test or from a program that you're working on. You guys should feel free to interrupt me anytime that something I say is unclear or needs more, I don't know, content clarification, detail, what have you. Okay. All right, so just a quick, I guess maybe audience check here. Has everybody at least heard of the update graph processor here? Or anybody who hasn't?
Not really. I mean, I've just heard the name. That's about it.
Okay, then great. This is actually pitched about the right level then. So to begin with, the update graph processor is and you'll see the same concept in the enterprise side that referred to as live table monitor, but we've renamed it for clarity in community. It is responsible for installing and propagating all table data changes within Deephaven query engine instance. What that means, like, nothing should be visible. No change should be visible that didn't happen under the auspices of the update graph processor. Otherwise, our consistency model, is violated. All right. It works by periodically refreshing a series of sources, which are these days just Java runnables, right? And then following on from there. So each source that you invoke is going to potentially enqueue a notification or many notifications. Those notifications are then processed in a dependency respecting order, and that notification delivery is the mechanism by which we actually communicate changes down the DAG all the way to the leaf nodes. So when we talk about dependency respecting order, what I mean is, for example, if a node, in the trivial sense, right? If a given node in the graph, is going to receive a notification, is going to receive it after its parent has already processed whatever data change it's going to process on the cycle. In the more complex scenarios, a node might have multiple parents. For example, a join depends on 2 source tables or 2 parent tables. A merge may depend on an arbitrary number of source tables, as might a partition by, right? And our framework presents the mechanism for expressing all of that and making sure that we only ever fire a given listener once per cycle. We only deliver notifications when they're safe to deliver. You guys mostly don't care about the details of how that's implemented unless you're building engine operations, but the basic idea here is that each notification keeps track of all of its dependencies and can be used to check those dependencies. All right. I guess that's probably adequate. The graph processor also supports terminal notifications, which we use for kind of post-cycle cleanup. Maybe we need to return some things to a pool that weren't safe to return until we no longer could be fetching previous data, or maybe you want to deliver, fire off some other kind of, hey, all the updates are done in the cycle, kind of a notification to some other process. And that mechanism exists for that purpose. It's fairly rare to use it nowadays, though, for anything new. Are we clear so far? Seems like it. So the thing about the update graph processor is that it is in fact parallel, or at least optionally so. There's a configuration property, I specified here on my slide, which defaults to 1. This specifies just how many threads we're going to use. By default, it's 1, so that there's a core refresh thread that does all the work. If we set that to be greater than 1, then the refresh thread is really just responsible for dispatching notifications to do. And you have, in my slide here, C, update threads that are actually used to invoke notifications. Now, the thing about this, right, is we're parallelizing this work, but how effective that parallelization is depends very much on whether you have adequate resources for the job, right, the jobs you want to do, and whether those jobs are in fact parallelizable, right? So, if you, I don't know, are doing other things that have to grab the Python GIL, you're going to achieve basically a parallelization of 1. You might as well not even bother with extra threads. If your source data all has to lock the same lock to read from some underlying table, not that our Deephaven underlying table is actually required to do that, then you're going to have parallels in factor of 1, right? So, we work extremely hard within the engine to make sure that you don't need to grab a lock to read a table. You don't need to grab a lock to do any of your kind of high frequency operations, right? So you might interact with a cache that has one, but usually we'll have a thread local cache in order to make that efficient, at least for the threads that live inside the update graph processor. But there's obviously nothing we can do about user code in all cases, right? If you're invoking some method on a model object that internally locks state, then you're going to have a bad time if you're expecting parallelism. Now, sometimes you'd really like to be able to do some work that happens without update processing continuing, right? So like a classic example is every time you execute a line of script code that blocks the graph processor from continuing, right? Implementation-wise, we have the update graph lock for doing this. You don't actually necessarily need to care about that class because you're not going to use it directly. You're going to invoke either the exclusive lock method or the shared lock method on the update graph processor object itself, singleton itself, and that they're going to get a lock via that you can then use to actually lock a section of code or whatever other pattern you're trying to follow. It's a reader's writer's lock in effect, right? So the shared lock allows multiple threads to hold the lock, which means that multiple threads can make progress doing read-only things. The exclusive lock is exclusive; only one thread can have it. The update graph processor itself holds the exclusive lock during the entire duration of the update cycle. So if you want the shared lock or the exclusive lock, you're going to be blocking the update graph processor from making any progress. That means you might be arbitrarily pushing out the latency of any query updates that you're hoping for. But again, there's a time and a place when you actually want to inhibit update processing, right? These are kind of fancy locks. You can test ownership on them. They are reentrant, meaning you can lock a second time within the same thread. And we have some patterns that for example, calling a method under the lock and then immediately releasing it. So trying to write safe concurrent code. So if you look at that functional lock or aware functional lock interface, you'll see those methods. And especially if you're working within Java, it's extremely convenient, extremely helpful when it comes to avoiding errors, like forgetting to release your locks. One thing that comes up from time to time, recently that Larry in the delivery of one of his first chain sets is the need to wait for table changes. So the classic pattern is, an asynchronous pattern, right? You listen for updates to the table. Okay, we have a table support a listen for updates method. You specify a listener, which is a callback. Whether you're in Java or in Python, there are appropriate interfaces for doing so. And that lets you consume changes as part of the update cycle, actually, right? So you'll just be, your listener callback will be invoked via notification from the refresh or one of the update threads of the update graph processor. But sometimes you actually, you don't want to follow that pattern, right? You might, for example, require the update graph processor to work for so you might be in a scenario where you already have the update graph processor's lock and you need to unlock it so that it can make progress that you need in order for you to proceed, right? So the general approach here is that you get a condition variable from the UGP's update exclusive lock, and I give you a little code snippet for that right here on the screen. Then you could always, or you could also just call await update on a table, which is basically going to block until an update happens. And it might not be the update you're looking for, but an update happens, right? If you do happen to get a condition variable yourself, you're going to have to use request signal on it in order to notify, right? So this is, kind of analogous to wait and notify, which you guys have probably encountered before with Java objects, but it's using a more explicit interface from the lock package, right? So condition support await and signal, which are effectively the same thing as wait and notify. They have different names so that they're not conflicting, right, with the ones that are built into object. The same rules apply, right? Just like you have to synchronize an object in order to wait on it, right, or notify on it, you also have to synchronize on the exclusive lock here in order to await on a condition or signal on a condition. And just as a sort of implementation detail, you cannot get a condition from the shared lock. It's just not supported by the underlying implementation, which is, wrapping at some point, at some level, wrapping Java's read write lock, right? I might actually give an example of how this works, but the key here is that if you're in a script, for example, and you'd like to, you can't make progress until some changes have been delivered under the update graph processor, you're going to have to get one of these condition variables or use the await update method on a table in order to unblock the update graph processor and allow it to make progress. Or again, use a listener for callbacks. Does that kind of make sense to everybody here, or am I kind of going too fast or too dry? All right.
So far, good.
Okay, great. Now, kind of the last slide I think I have completed in this case might be this one here about the logical clock, right? So the update graph processor has associated with it an instance of a logical clock, right? The logical clock is exactly what it sounds like. It divides time into logical units that have nothing to do with wall clock time. Each cycle of the update graph processor is divided into an updating phase and an idle phase, and is denoted by a clock step. So what the way it kind of works is we bump that atomic counter once to enter the updating phase of the cycle, and we bump it again to enter the idle phase of the cycle. So you can read it atomically to figure out what phase you're in right now, as well as what step you're in right now. And this is useful for a lot of concurrent operations where you don't want to try to acquire the lock. Go back kind of to my catch-all slide so we can kind of just hit the talking points. I will maybe finish the slideshow after the talk, but I'm sorry, I'm a little bit less prepared than I wanted to be, which is usually the story of my life, which is probably why Colin's smiling. I'm kidding. All right. Let's talk a little bit about how and why that is used. Okay. The engine supports the idea of concurrent snapshotting of data or concurrent initialization of table operations, right? And the key here is you can read data optimistically without acquiring the update graph processor's lock, as long as you're willing to verify that you can prove that you read that data consistently and throw it away if you can't prove it, right? So the pattern basically looks like you read the value of the logical clock, you read all the data you want to read, you reread the value of the logical clock, and if it hasn't changed, your data is good to go. Now, it's not actually that simple, but it's depending on what you're trying to do, but it's almost that simple in a scenario where all you want to do is get a consistent snapshot of data. So which is sometimes a pattern. It's not a pattern that often because we do live in a real-time world and consciously and deliberately, right? But if all you want to do is get a consistent snapshot of data, that is sufficient. There are some rules to that in addition, right? So if you are in the updating phase of a cycle, you need to use our table interfaces for reading previous data, which means that you have to read the data that was correct as of the beginning of the cycle. And every single Deephaven table and row set and column source knows how to present that previous state during the updating phase of the cycle. If you are instead in the idle phase, then you would need to read current data, using these sort of slightly more accessible interfaces for accessing the current state of the world, which would be the state as of the end of the updating phase of the current cycle, all right? The reason I said this gets a little bit more complicated is if you're trying to initialize a table operation, you're typically in a world where you're trying to join the update stream, the stream of changes that table has delivered or will deliver, without missing any state, right? So in that case, you actually have to look at your immediate parent node and check its last updating step to determine whether you're it sort of subdivides the cycle into, for the purpose of your operation, into 3 phases instead of 2, right? So you have the pre-update phase for your parent, you have the post-update phase for your parent, and you have the idle phase, right? And whether you need to use current data, previous data, or current data or previous data actually depends on your parent, not on the cycle itself, right? So the key here is that you need to get a consistent snapshot of data. If you're in the pre-updating phase, you need to do that before your parent delivers a notification. And also additionally, if your parent never delivers a notification, you need to get it done before we move on to the idle phase, because your previous state is only valid during the updating phase. So it's a little bit complicated. That all of this is frankly codified for you for almost all operations in some classes that implement snapshot control, which you can find in the construct snapshot class. And even the engine itself is actually using construct snapshot and snapshot control in order to implement these concepts, right? Because it's legitimately difficult to reason about and get right, and so we have a kind of a well-trodden path and pattern that we use for most things. It gets a little hairy once you start talking about multiple sources of data. Most engine operations that have multiple sources of data are actually not concurrent for that reason, but it can be done. It isn't often done. So things like merge or join actually still require you to get a logjam monitor, an update graph processor lock before you initialize them, right? Kind of moving on a little bit to just talking further about operational initialization. There are multiple threads available in the pool for parallelizable initializations. It's maybe not used all that heavily, but there are cases where it's valuable. The main places where this stuff is used right now would be if you're instantiating a kind of a parallelizable pattern using partition by and applying to the different subtables of a partition, or if you're doing an update or a where. Well, update is currently parallelized, select is currently parallelized in some cases. Where will probably likely soon be parallelized, but the code hasn't yet been ported from enterprise. Again, all that kind of goes out the window if you're touching Python, because we don't want to interact negatively with the GIL and deadlock. There is work kind of to be done maybe to make that better, but that's sort of the state of the art right now within Deephaven and within JPY. I went over that awfully fast. Anybody have any kind of questions so far? Okay. Let's move on and talk a little bit about unit testing. Do's and don'ts. Let's start with a first really big don't. Don't sleep. Right. We almost never want to sleep in the unit test. It usually implies that something is wrong in the pattern that we're following, and that we should be doing either the test is a bad test or we should be doing following some other pattern. Right. There are testing tools built into the update graph processor right now that allow you to deliver updates in another thread, and then wait for those updates to be delivered in your primary thread. And that's often the mechanism we want for something like this going forward. Do's: do use that testing framework. Don't sleep. Don't introduce things that might fail on concurrency or otherwise be racy and cause CI nightlies to fail, right? So yeah, I think this is unfortunately a little bit light at the end here because I didn't prepare as much as I wanted to. So I'd rather just kind of like open up now to kind of talking about any problems you guys are having and kind of go into basically any details you guys are interested in exploring further. Are there any questions at this point?
I have a question,
Absolutely.
Ryan. And forgive me if this is outside of the scope of the presentation, but what are the different concepts someone should be familiar with for parallelizing kind of like historical analysis and like static data? Because I know there are some like table maps and stuff like that that can apply to, that will parallelize historical analysis versus real-time parallelization.
So there's a little bit of a there's a bit of a dichotomy there between enterprise and community in terms of terminology and in terms of what's supported right now, Morris. And I know that you're mostly working in the enterprise world, so I don't want to kind of, you know, stumble too much over the wrong things, right? So when you say table map, I mean, that's like the concept exists in community, although it's being revised right now. You know, usually you achieve those with a by external enterprise, and community you do that with a partition by, but it's fundamentally the same operation at this stage, right? And so there's an operation called apply on a table map that if you've enabled the operation initialization threads to be greater than 1, right? We can actually, once you've got your table map, once you've partitioned the input table into many subtables, we can apply a given query operation to all of those subtables potentially in parallel, right? So maybe you split your universe into 1,000,000 pieces, and you've got 10 threads to throw that at, right? We can churn through those 1,000,000 sub operations, you know, 10-wise parallel, right? In that model, right? It's a pretty reasonable thing to do if you have truly distinct workloads, right? Like, I mean, if all of your if all of your input tables after the partitioning are not sharing any resources, then it's a pretty efficient thing to do. It's not necessarily going to be a win for small operations, just because the cost of that startup of parceling the job out into smaller pieces might exceed your benefits from being able to do some of the work in parallel. All right. But for bulky things that are fundamentally not going to run into fault sharing or concurrency limitations, it can be a huge win. And so again, it's partially on you as the user to understand your data, its access patterns, and the nature of the operations you want to apply. And of course, we can go to specifics if there's like a case you want to consider. This is a good forum to go over it.
No, I don't have a specific case right now. I just know it's something that comes up a lot. But thank you for delving into that a little bit.
No problem. Anybody else have anything they were curious about?
So obviously, it's a lot of information. What kind of, so earlier on in Deephaven's, I guess, life cycle, what kind of like, how did this update graph processor and all these processes look compared to what they look like now? How has it kind of evolved over time, and for what reasons were particular maybe large changes made?
That's actually a terrific question, JJ. Thank you. So in the early days, for one thing, there was only an exclusive lock. So the introduction of the shared lock is a few years old now, but it's still relatively new in the life of Deephaven, right? And obviously we added it because we thought it was valuable to be able to inhibit update processing while still doing multiple jobs in parallel on multiple threads. You know, so there's certainly a time when you want to do that. I mean, even talking about snapshots, right? You know, say you're trying to do multiple concurrent snapshots. The fallback for a concurrent snapshot is always to acquire the lock. But say, you know, you're doing your snapshots in order to paint a GUI, you don't need to lock out of the threads that are doing the same work, right? So each of those threads should acquire a shared lock, and will, by the way, it's built into the helpers that we have, right? In order to allow you to make progress concurrently, right? So again, that all that discussion around kind of the concurrent snapshot model is fundamentally one about optimistic concurrency, right? you're hoping that you've got a consistent read of the data. And if you don't, eventually you give up and you acquire a lock, right? But that's always the shared lock in this case. Other things that have definitely changed. So with the introduction of parallelism within the update graph processor, we had to massively revise our dependency satisfaction model. The initial approach was vastly simpler, and it basically revolved around having a strict total ordering of all of the installation of sources and listeners throughout the DAG, the directory acyclic graph. So you would basically, as you add root nodes, you're going to number them. As you add listeners, you're going to number them, and you're always going to deliver notifications effectively in that order, right? So you're going to invoke a root node, you're going to deliver all of its notifications, top to bottom, and then you're going to invoke the next root node. And so the nature of that was, quite a lot simpler from a correctness standpoint, right, and from a accounting standpoint, but it didn't allow you to parallelize, right, because we were doing totally ordered delivery. And so with the introduction of, parallel update processing, right, we had to go to a new system, which is basically kind of a tree-based system, right, kind of reversing the way up the DAG, right? So, as you've got your source nodes, obviously can't have any dependencies, and so we actually will fire them all off in parallel, right? And actually that's a relatively recent improvement that we made, let's say in the last year and a half. Previously to that, they were actually still done effectively single threaded. Then when we check our dependencies, right, we're basically looking up the DAG to ultimately to our sources to say, hey, look, is my parent satisfied? Am I able to deliver my notifications because I know I'm safe to do so? And when we talk about is my parent satisfied, right, we're saying like, look, has my parent already had it, whatever updates it's going to have on the cycle, or can it prove that it's not going to have any? And we actually, so we basically ask this question of our parents, they ask the question of their parents, and so on and so forth up the graph. And then we remember those results so that we don't keep asking those questions and create some horrible n-squared implementation, right, where that tanks performance. So let's see. So we talked about the introduction of parallelism. We talked about the evolution of the dependency system. We talked about the introduction of the shared lock. The condition itself, actually, the whole request signal and support for waiting on changes via the update graph processor, that is a relatively, or it wasn't there in the beginning. It's still a relatively old addition, but it's been there. But it's still new, right? Newer than some things. Let me think about what else has kind of evolved over time and why. We simplified the model at some point to use only a single clock cycle for the entire DAG each time. That was part of that. Part of that goes with what I was talking about in terms of being able to parallelize the. That was one of the impetuses behind being able to parallelize the refreshes of the source nodes, right? We originally would have a clock tick for every single source node in the DAG and basically handle that source node's updates together, and then handle the next source node, handle all of its notifications together, and so on and so forth, right? So you were basically treating the DAG as a series of I mean, not trees because they still potentially have diamond patterns within the dependencies, right? But you still had a single root in each case if you look at it that way. Whereas now it's really truly multi-rooted, even within a single update. And that has the advantage of if you've got multiple tables that are kind of advancing in lockstep, or you can make them advance in lockstep, you get a nice kind of consistent view of the data, right? I mean, not just consistent from like a Deephaven, provably correct standpoint, but also consistent in the sense that the data that arrive together actually gets delivered together kind of standpoint, right? So that's another kind of improvement. Initially, it was kind of enabled under a refresh all tables flag, but at this point, that is the default and only mode for how to proceed. One other kind of significant change that's happened is initially the way we worked was partially because we were sort of separating the global cycle into smaller subcycles like that. We would have kind of pauses potentially between the cycle where we would release the lock and allow other processing to proceed. Because that was called the intracycle yield, but I don't believe we're doing that anymore at all, or it's off by default certainly. But also, the way that we controlled the frequency of the cycle was a little bit different. You basically had rather than a target total time for a cycle, you had a target interval, right? So you would do some work, pause for that target interval, and then do more work, all right? And so, if your cycles were very long, you might actually have a longer latency between delivery of changes than you really wanted, right? So, but with the newer approach of having a target cycle time, if your cycle say uses, I don't know, maybe you're looking to have a target cycle time of once you want to update once a second. If your cycle uses 900 milliseconds, you're going to only wait 100 milliseconds before you start working again, right? In the old model, if your cycle use 900 milliseconds, you'd wait a second, and your updates would actually come 1.9 seconds apart. And of course, that's sort of an optimistic description, right? Because obviously there are workloads where folks have cycles that are much longer than once a second. And of course, people who've tuned their system well enough that they can have cycles as slow as fast as 100 milliseconds or 10 milliseconds. It kind of all depends on the resources you're willing to throw at the problem, your data change rate, your latency budget for your application, and your parallelism. I think that might be the full set of things I can think of myself off the top of my head, JJ, but it's likely pretty close to complete. Oh, actually, I thought of one more thing. We've got more instrumentation that allows you to determine how much time you spent as part of your update of your operation initialization waiting for locks. So we are a little bit better about reporting lock hold times and so on and so forth.
Which log does that go into?
That would be part of the query performance log or query operation performance log. I forget which, actually. It's probably the QPL, actually. Obviously all this stuff is also instrumented as part of the update processing log, the UPL, and that log gives you aggregated statistics associated with each node in the DAG. Usually over a minute interval. So we'll be able to tell you kind of cumulative over all the cycles that have been processed within this minute or whatever our interval is, right? How many rows were added, modified, removed, shifted, how much time did we spend doing I/O, how much time did we spend doing using CPU, either in user space or in kernel space, how much did we allocate, and so on and so forth.
Right. Any other questions?
Yeah. You mentioned that, for smaller use cases, trying to do concurrency is potentially not beneficial.
Mm-hmm.
Do we have any examples of customers, trying to use concurrency in either a negative or positive way that, might be useful to highlight?
So that's a good question. I mean, I would almost want to defer to some of the DHE folks who are embedded in professional services roles at the customers, if they can come up with examples that are, if you're speaking from a communication standpoint, right? If they can come up with examples that are sufficiently anonymous that we could talk about or anonymized talk about, right? I mean, I can tell you that we have at least one of our customers is doing some extremely heavy lifting using parallel update threads, over table maps. I know that in their case it's sufficiently bulky to be meaningful, right? But again, I mean, the classic example is let's say I want to do work over the entire options universe, right? And I want to split my jobs per symbol, right? I don't actually expect that, and maybe you're handling a couple hundred rows a cycle, right? I'm not sure that you're going to get much benefit by splitting into 1.5 million jobs per cycle, right? Just the cost to create all those things and queue all those things and then pull them out of queues and so on and so forth is excessive in that kind of scenario, right? Whereas maybe you've got, you're able to split your universe into 10 pieces and each of those 10 pieces is a million rows or 10 million rows a cycle. Well, then you're going to get you might be able to get a meaningful speed up if there's not any kind of concurrency issues there, right? If they're not sharing locks or sharing resources.
Yeah, one example of something that came from working with a client is a model farm.
Yeah.
Which is basically a thread pool where you can have tables feeding in data at a very high rate, but you have calculations that happen slowly. And the model farm will let you grab the latest snapshot of the fire hose of data coming in. Then you can do these elaborate calculations on it, and then you can spit that out to new tables at the rate you can generate it. And that's one case that is out there.
But this, part of thinking about this gives me, some ideas for some graphics we could put up if we, I guess it kind of depends on how much detail we want to go into in white papers or whatever, right? But we could do some really nice graphics about things like a concurrent initialization, for example, and how that interacts with the logical clock. But I'm not sure if there's an audience for that level of detail.
I mean, I'd be interested.
Glad to hear it, Morris. What else can I talk to you guys about?
Oh, I had a good question. I think someone, it was Charles, once said that like if you have a partition map, or for my case it was table map,
Yep.
and then in the query you merge like those tables after doing some operations on them, then I believe it was because of the merge, the updates won't be parallelized because it considers it one table after initialization, or something like that. Does that sound?
Yes. So table maps right now support an interface. There's sort of two kind of ways to look at them as tables, right? One is the as table method, where you're basically treating it as a table, but it's really a proxy through to applying table operations to the individual subtables that make up a table map, right? So you take your table map, you call as table on it, you get a table back, but that table really just proxies your operations, right? So in that case, you're getting parallelism. If you call merge instead, you're basically getting sort of the equivalent of if you use the table tools method merge or the table factory methods merge, right? If you're on community, which means you have a single table that views all of those subtables that you included in the merge as sort of stacked, right? So table 1 is here, and table 2 is here, and table 3 is here, and 4 is here, and they all tick within their regions of the address space. But it's still a single table from this perspective of downstream operations, right? So you're not going to be able to get any parallelism on delivery of notifications downstream of that. I mean, without obviously further subdividing the DAG by having multiple operations that depend on that merged result.
So then, so it sounds like are the internal operations going on this table map proxy still parallelized, and then everything after
Yes.
it is kind of okay. That was,
yeah. It's the merge. The merge that says, look, give me a single Deephaven table, not a proxy to a table map, right? That gives you then only one unit of parallelism at that stage, right? So the merge itself is a single listener or has a single listener, or sorry, a single merge listener, right? That sits downstream of listener on each of those subtables, right? Kind of funnels all that together into a single node, single table. And then again, you can apply subsequent operations to that, and those things would be potentially parallelized, right? But you're still going to be gated on the merged tables,
right?
Tick on a given cycle. It's delivery of notifications from all the upstream tables before you can apply those subsequent operations, right? And again, it's one table that you're operating on, not n tables that you're operating on, not many tables that you're operating on. So it's fundamentally going to be a single operation, unless we can do intra-operation parallelism, which is again still right now relatively rare within the Deephaven query engine. Update supports some of that. Where supports some of that on the enterprise side, but in general, it's not something we do a lot of yet.
All right, thank you for explaining.
Right. Anything else for Ryan? All right. Thanks, Ryan.
Thank you, Chip. Thank you, everybody else. Great questions today. Appreciate it. Bye all.